Swayam Prabha. Digital India. Educated India.
We have already looked at energy resources, and we saw that we have stocks, fossil fuels, and we have flows, renewable energy. We saw that there is sufficient renewable energy to meet our requirement. Now the question is, we have sufficient renewable energy to meet our requirement, but each of these renewable energy sources needs technologies. Those technologies need materials. Do we have enough materials to meet the energy requirements, or will we end up in a problem related to materials? So the issues that we would like to address, one is, will we run out of materials? Can we create a closed loop materials system? Which renewable energy materials will be constrained and what will be the impact? We are not going to completely answer all these questions, but we will look at the way in which we can analyze this and what are the typical types of materials and how they are looking at it. So if we look at the materials, we find that of the significant amount of our CO2 emissions are accounted for by some of the most energy intensive and carbon intensive materials. If you look at materials, we are looking at steel, we look at cement, we look at aluminum, paper, plastics, and these accounts for the largest chunk of the carbon emissions. It's about 10 gigatons of CO2 out of the total of 28 gigatons of CO2 in a particular year. I think it's 2008. And this is from the paper by Alwood. You can look at this paper for more details. So if we look at the periodic table, which I am sure all of you are familiar with, you have studied it at some point of time, either in your school or your college, and you can see that there are several of these materials, including some of these rare earths and some of now these materials which are becoming important for batteries, for storage, for photovoltaics. You have this whole set of materials which are coming in for the photovoltaics, for the lead acid batteries, cadmium telluride. Then you have the other chromium, nickel, cobalt. Then you have lithium. Then you have these materials which are used for hydrogen storage, and many of these materials are located in some regions and in a few countries, and they also involve significant amount of energy use in their extraction. So when we look at materials, we can think in terms of material efficiency, and this is from the paper by Alwood. We can try and design so that we use less materials. So we can, this is called dematerialization. You know, look at your cell phone or look at a motor, see how much steel and how much metal is going into it, see if you can have the same functionality using less metal. We can also replace the substitute energy intensive materials by less energy intensive materials, materials that are less carbon intensity. So that is we can do dematerialization, we can do light weighting, and now with nanotechnology we have the advantage that we can actually have designer materials which have the properties that we require. For instance, it's been told that, you know, if you look at the Eiffel Tower and you look at the weight of that Eiffel Tower, today if you have designer steel with nano composites and engineered steel, you can actually, we could reduce the quantity of steel that is required with the same strength, and we can get a much more lightweight Eiffel Tower with using less materials. In general, when we look at the production of a material, we can look at the production going to the and you have the at each stage of the production there would be some scrap. We can recycle that scrap. That when we look at the demand, and then the after the post demand, when it is used, it can be recycled and some part of it. So we can try to see if we can have this entire thing as entire loop as a loop which is closed, and we use relatively less amounts of virgin material, and we can try and recycle at each of these stages. If we look at the global material use, you will see that energy intensive materials account for about 50% of the industrial energy use: cement, steel, paper, chemicals, fertilizers. And also the interesting thing is that most of these now these materials are being consumed by the developing countries. There are much higher growth rates in the developing countries. We have, if we look at any of these materials, we can plot. If you look at, let's say, steel use per person, and we look at the status of the country in terms of GDP per capita or GDP per person, you find that this increases with income to a point where it stabilizes and then maybe declines. This is something like this is called the Kuznets curve. So most of the developing countries are at this stage where there is this growth. Developed countries have already gone where you have already produced all the steel, you have your infrastructure is already created, you have the number of cars and the kind of things which is there, and then the number of it starts declining. And so that's the kind of thing, and I'll just show you some of this trends. So if you look at steel, you see different countries: North America, Europe, you can see China and India over here, and you can see that this is corresponding to something like we go to a stagnation level which is of the order of about 450 kgs per person per year. So it's an apparent consumption as a function of income, high growth rates for developing countries, and it goes to saturation. There is an implications on the global energy use. This similar thing you can see, for instance, for cement. You can look at the kind of different levels at which you have these developing countries which are growing. In these cases, it's more or less saturating. Of course, it's saturating at different kinds of levels. And this is sort of global demand normalized. You can see that there is an overall growth. Ashby has come up with this scientist in UK who's created these kind of design plots, and these design plots are extremely interesting in terms of when you look at a particular characteristic. For instance, you look at the Young's modulus, energy per meter cubed, and if that is the requirement which is for a particular application, and we are choosing between the metals, polymers, ceramics, and you have the embodied energy, which is the total energy required to create that material and to extract it and to make it available from nature per cubic meter. So based on this, we can use with this we can decide between different materials and see what is the implication when we are making a particular choice in terms of what is the amount of energy that is being used. So this could be used, and we can have similar kinds of plots giving the carbon intensity of these. This is another plot which is talking about the strength, and the strength in terms and the embodied energy. So these are interesting design aids which can be used for us to choose less energy intensive materials and less carbon intensive materials for a particular application. And so, you know, we will, when we talk about embodied energy and we do the life cycle, we will look at this a little more in detail. But one can look at different types of elements and see what kind of energy is embodied and what kind of efficiency is there. So, in general, what has happened is that one expects that with materials, as as the demand increases, and if in most of the materials we are looking at a finite stock. So, there are stocks, but then there are possibilities of substitutes, and with technology improvement it is possible that we can have less use of the material, but in general what one expects is that we will run out of materials. And so, there was this debate and you can see this there is a very interesting bet which was there in literature, and you can see in Science in there is a journal article published by Professor Julian Simon in 1980, and he basically felt that planet's resources are not finite. There has been ecologists and environmentalists were saying that we need to look at materials getting over, we need to look at the resources, and he said that planet's resources are actually not finite. There on the other side of the bet were Malthusians, Paul Ehrlich, John Hart and John Holdren, and they have been saying that we have one world, one earth, and finite resources, and we need to conserve and use our resources efficiently. So, Simon challenged through an open challenge, saying that if the scarcity is due to population growth and the prices of all natural resources, grain, oil, timber, metal should rise at any future date. And he said that he is willing to bet anyone, because he believes that technology and human innovation is such that there is no scarcity caused by human efforts, and he said that he was willing to bet anyone that prices would decline at any future date, and he made an offer that any natural resources can be picked at any future date. So, when this challenge was issued, Paul Ehrlich and John Hart and John Holdren took up the challenge. Ehrlich, John Holdren and John Hart accepted the challenge in October 1980, and they chose the following materials: chrome, copper, nickel, tin and tungsten, and they bet a token amount of $200 each at 1980 prices on these 5. So, a total of $1,000, and the idea was that in 1980 at $1,000 they bought a certain amount of this, and the idea was to, if the future date of 1990 was picked, and it was said that whether the value would be more than $1,000 or less than $1,000. If this was more than $1,000, then Simon lost the bet, and Simon has to pay that difference to them. If the prices actually declined, if it was less than $1,000, they have lost the bet and they have to pay Simon. So, what do you think happened? In this particular case, actually Ehrlich, John Holdren and John Hart actually lost the bet, and you can see these are the commodities which were mentioned. You can see that this was in the 1980, and when you look at 1990, you find that actually the prices went down. So, essentially what happened is that you can see that this is what happened in 1980, this is the situation in 1990. And so with the result that this of course didn't prove it conclusively, because this goes through ups and downs, and there was an economist article recently which said that it just so happened that he was unlucky to choose the years. If it had been some other years, then this would be the kind of situation. But the fact remains that overall there are two trends which are there. One is that there is a problem in terms of scarcity, but also with technological innovation and volumes, the cost reductions are there. So over a long time period, we have seen very significant reductions in costs of materials. So you can see, for instance, if you look at copper, real price of copper has been going down. And so it is not clear. There is an issue of scarcity, but there is also an innovation and possibility of technological improvements. And so when we talk in terms of materials, we have to be aware of scarcities in the short term, but it is not completely apparent that this will necessarily result in extremely high prices. There could be backstop technologies and other options which are available. So for all of these materials, we can use the same static R by P ratio, or we can use something like the Hubbard's curve if you want to estimate time periods. In many of these cases, these are all these price trends. In many of the cases, if you see, we can actually look at what kind of what is the distribution of these materials. So sometimes regionally, some countries have, for instance, if you look at lithium, it's only available in a few countries of the world. So the control of these materials and this could involve getting an advantage, and then the industry and the development may be affected by it. So we may need to look at substitutes. So with this, we have seen, we've got a quick introduction of the kind of materials that are used for the energy sector. We looked at with development that material use per capita will increase and then saturate and maybe then decline. And then there could be possibilities in terms of substitution by more energy efficient and low carbon materials, and then we can look at it. It's not essential that scarcity of materials always results in increase of price. Historical trends show that there is also a scope for innovation and technology improvements where prices may actually decline with time. With this, we end the portion on materials. For those who are interested, there are more details in some of these papers. You can look at the GEA, you can look at the papers by Allwood, and about the bet, you can look at John Tierney's original article in New York Times, which gives you about the betting on the planet. In the next session, we will start with looking at the historical way of the mine manager's problem. If you own a mine, how much of that mine should you allow to be used every year? And we will cast this as an optimization problem and see how a resource, a coal or oil or gas, how it should be mined and distributed over future generations. Thank you.